Hi. When you have used ChatGPT, you might have wondered what is the technology that goes behind this? How does it actually work? All the modern large language models like GPT or Cloud, Sonnet, or any other large language model works by using a technology called transformers. Transformer was introduced in the famous paper from 2017 called Attention is All You Need. It has huge number of citations. In this video, we will attempt to understand transformers by oversimplifying it. My name is Dr. Sridhar Panat. I'm a PhD from MIT. And in this video, we will try to understand the different parts of the transformer and how does it allow us to build technologies like ChatGPT from the basic idea of next word prediction. So here, let's start with a very small value of temperature. Just observe what is happening to softmax here. You see the value which is highest is taken close to 100%. All the other values are taken close to 0%, which means if for the same input, like for ChatGPT, you might have noticed if you provide the same input, ChatGPT does not provide the same output. Output varies, right? It's not deterministic. There is a certain amount of probability. And you can see the effect of temperature on this probability. So first, let me click, let me click generate. With temperature being 0.2, let me click generate. Then you can see that almost always the top guy is being picked. Top guy meaning whichever is the, okay, let me select another example. Okay, let us do the calculation. Now let's keep the temperature low, 0.2, and then click generate. So here you can see that always this top guy is picked because the probability of this top guy is 95.52. So even if you click generate again and again and again and again, the top guy with the highest probability will be most likely picked. But of course, sometimes the other one will be picked depending on how the output probability distribution is coming. But you can see that it is very deterministic. The output is very deterministic, meaning almost always the highest probable predicted next word is picked. But what if the temperature is very high? Then you see the or rather maybe something like 7, 6. You see what's happening to the probability distribution as I'm changing the temperature. The probability distribution is more evening out. So it's like 3%, 3%, 2%, 2%. So all of these words have some probability to be picked as the next word. So if I click generate, it won't always be the top 1 or 2 words. It could be the 10th word in the prediction list. It could be in the 15th word or 100th word, depending on the probability distribution. Because all of these words have kind of equal probability to be picked from. So now this word is picked, not the top words. But if the temperature is, let's say, 0.5, then or rather something like this, then maybe the pick or something like this, then pick will happen from these top words, because as you go, the top word has 3.52% probability. The bottom one of these bottom words, the bottom most word is the 12,000, the vocabulary size, that word. But here mostly the top few words will be picked. One of the top few words will be picked. If temperature is very, very low like this, almost always one of the top 2 words will be picked, top 2 or top 3 words. So it's very, very deterministic. So this is what the temperature does. So people often say that if you increase the temperature, the LLM is more creative. So if temperature is very high, the probability distribution of the possible next words are kind of evened out, so that you can pick from, the model may end up picking from one of those words. So you will get unexpected output. But if you want very deterministic output, you have to set the temperature to be less than 1. Then it will be deterministic. So that is what is shown here. Temperature greater than 1 meaning creative and less than 1 meaning deterministic. So this is all about transformer model. I just want to show one last diagram which will help you visualize this whole transformer setup in just one single figure. So in this video, I'm just summarizing here. We saw the transformer architecture. We saw that there are 3 modules in the transformer: embedding, transformer block itself, and the part which produces the output probability. In the embedding, what happens is the input text. So from embedding, the input text is converted in 4 steps into the final embedding. So first is tokenization, where the sentence is split into words. Then the token embedding is done, where the English words are converted into a 768 dimension vector. Then positional encoding is also added to the token embedding to produce the final embedding. Why is positional encoding important? Because if the word is something like all animals are dogs versus all dogs are animals, although the words are the same, the position is kind of changing the meaning. So this is very important. And then this final embedding is used in the multi-head self-attention, where we calculate the query key value matrices. And using the query and key, we first create the attention score, which was a 6x6 matrix because we had 6 tokens, right? So we had a 6x6 matrix for the attention score. Then the attention score is converted into a mask, where the top right triangle is removed, or it is converted into minus infinity, so that when we apply softmax, first row will have only one word with value equal to 1. Second row will have not one word, one number. Second row will have 2 numbers whose sum will be 1, and third row will have 3. Remaining 3 will be 0. So this will be the output. Now this output softmax distribution is sent into a multilayer perceptron, which is nothing but a simple feed-forward neural network, where we are doing 2 linear transformations and using the GALU activation function. So first, the 768 dimension is scaled up by a factor of 4. Then after activation, it's again scaled down by a factor of 1/4. And then this is used in the final part, where the last word, in our case, I think the last word was 2 in the example that we picked. The last word has a certain embedding, right? That is used for predicting the output probability. So first we convert it into a set of logits. So the 768 dimension last word is kind of projected into the 12,200. I forgot what was the total number of tokens, but basically into the vocabulary space. And each token in the vocabulary has a probability distribution, or rather it has a logit value. The logit value is divided by the temperature, and then we take the exponent of this. If the temperature is very high, then the exponent value will be low, and this will affect the softmax probability. So the exponent, which is obtained after taking the exponent of the logit, is converted into a softmax values. So if the temperature is very high, the softmax distribution for all the possible next words will be very even, meaning any word can be picked from the set of possible words, set of possible next words. And this is where people say when the temperature is increased, the creativity of large language model increases. If temperature is much less than 1, it means the softmax distribution will be very much favored towards the top word or the top 2 words or something like that, which means almost always among the distribution of words that are possible for the next word, the top word or the top 2 words, one of those words will be picked, which means the output will be very deterministic. And if the temperature is 1, the output of softmax is unaffected by the temperature, because when we divide the logit value by the temperature, it is logit value divided by 1, which will remain as the logit value itself. So this is the transformer architecture in short. I am definitely sharing the link to the Poloclub transformer explainer in the description. Please go through it. And if you have any insights, or if you have faced certain difficulty in certain parts of the transformer, not just from this video, but also from your attempts to learn transformer in general, if you have faced any difficulties, feel free to comment it, because I think if we can initiate a lot of discussion around this, people can provide more and more insights about different ways in which transformer works. I have personally seen that each time I read the Attention is All You Need paper, I end up understanding something new. Although the paper itself is a relatively short paper, it is so dense and it's so difficult to understand, because transformer itself is a very complex yet very beautiful architecture that people have invented. So I hope you enjoyed this video. We'll be coming up with many such interesting content. So take care and see you then. ChatGPT works based on the idea of next word prediction. So if you are given an incomplete sentence or even a complete sentence in the form of a question, and if you feed it to the ChatGPT, what it tries to do is to predict the next word, and then you add the next word to the existing sentence and create a larger one, and then it tries to predict the next word. So next word prediction is the basic fundamental thing that goes behind how ChatGPT produces its output. So you might have noticed when it creates output, it produces the output word by word. It does not give all of the entire paragraph all at once. Sometimes it's so fast, it will appear as if the entire output is coming at once, but it's producing it word by word. So the first step that goes behind is called tokenization. So I will go into the details of what each of these things are in the most oversimplified manner so that you are not overwhelmed. So I'll first walk you through this interactive unit of transformers, and this is by Poloclub. I will be hosting a link to this transformer explainer in the description. But basically, the sentence that we are inputting into ChatGPT in the form of the prompt, it is divided into something called as tokens. This is what you see here. Tokenization is also very much analogous to splitting a sentence into words, although that is strictly not the case. Then these tokenized words are represented in terms of certain numbers in the form of vectors. We will also come to that. So the way I'm going to cover this structure of transformer is I'll first go into the individual parts of this transformer, and then I'll come back to this interactive module and I will walk you through the interaction so that you can visually see. But here, let me just randomly click so that you can see individual steps detailed in the form of these beautiful visuals. So there is token embedding that is being shown. We will show that in the lecture. Then something called as self-attention. So this is multi-head self-attention. We will quickly see what this means, and then how this self-attention is manifested, or how it is appearing if you have a set of, let's say, 7 words. So it will look like a 7x7 square matrix. And then finally, how all of this is used and how this passes through a multi-layer perceptron, which is a feed-forward neural network, and how does one predict the next word based on certain probability distribution. This is what we are going to see. I am pretty sure if you are listening to the transformer structure for the first time, you are probably a bit confused, but we will make it very, very clear. So let's have a look at the structure of transformers part by part. So firstly, the model that we will be looking at today is GPT-2. Currently, we have ChatGPT, GPT-4, 4.0, we have GPT-4, GPT 3.5. So this is a very primitive, compared to what is available today. This is a very primitive model. It has 124 million parameters. The models today have 100 billion or so number of parameters. So this is a 1 by 1000 size model compared to what is available today. And the way in which these models work is the first step that which helps you process the input is something called as input embedding. Input embedding has 4 steps. In the first step, the input sentence is converted into tokens. This is called tokenization. So if the input sentence is something called data visualization empowers users to, it's split into 7 tokens. So this is the first token, second, and up to, this is 6 tokens, not 7, into 6 tokens. Then one thing you can notice here is the word empowers is split into 2, M and powers. So this is one small example to show you that the split of sentence into words is not strictly word-wise. It's based on something called as tokens. But I don't want to go into the details of how exactly the split is done. For all practical purposes, just imagine that the sentence is split into respective words. And the vocabulary of GPT-2 has large number of such tokens. And in fact, the GPT-2 vocabulary has 50,000 plus unique tokens. So each of these are tokens, right? And each of these look unique. There are 50,257 such unique tokens in the vocabulary of GPT-2. And each of those tokens has a unique ID, which is a numerical value. So here, the token, which is in English, is converted into a corresponding token ID. And this token ID is a vector representation of this English word. And the vector has 768 dimensions. So let's say the English word is data. This data is converted into a vector representation, which is the numerical representation of this English word. And the dimension of this is 768 by 1. And this could be something like 0.1, 0.34, minus 0.2, whatever. Like these are a bunch of numbers, and there are 768 numbers in the representation of this vector, of this word. And this word is basically the token. And this particular token has an ID 3145. So when GPT-2 is referring to token number 3145, it is basically the embedding of the word called data. And the shape of it will look like this, 768. On top of all of this, there is something called as positional encoding. It encodes or it embeds the fact that the word data is appearing in the 0th position, because the counting of the position starts from 0, 0, 1, 2, 3, 4, 5. And this positional encoding basically adds this additional information that the word data is appearing in the first position, or rather 0th position. And why is this important? It's important because consider this sentence: all dogs are animals. And consider another sentence: all animals are dogs. So the meaning, this is a very meaningful sentence, whereas this is not. And why is that the case? And why? How do you capture the fact that these two sentences have completely different meanings? By looking at the position information, because the words that are present in this sentence and in this sentence are exactly the same, but the position of dogs and animals are switched right over here. So that is why the information of position of the words are so important to construct the meaning of a sentence. So that is what is done in the third step, which is positional encoding. Don't go into the details of how the position encoding is done. And in the final step, this is the final embedding, which is simply the sum of the token embedding plus positional encoding. So this vector is added with this vector. So this is a 768 dimension vector. This is also a 768 dimension vector. The resultant final input embedding is also a 768 dimension vector. So these are the 4 steps involved in input embedding, where the input sentence is converted into a set of embedded tokens. Now let's go into the next step in the transformer. In the next part of the transformer, which is called as multi-head self-attention. I understand that this image looks a bit scary. Don't worry about that. I will make it as simple as possible. In the multi-head self-attention, this is, maybe you can consider this as the most famous part of transformer that makes it what it is today. I will explain why there is multi-head and why is it called as attention. So firstly, this multi-head self-attention part of the transformer has 3 subparts. It's called query, key, and value. These are 3 matrices, which you can see in this figure. So firstly, let us look at the embedded input, right? So we had 6 words, and each word had a dimension of 768. So now this input, this whole embedding of the entire input sentence, which had 6 words or 6 tokens, is represented by a 6 by 768 matrix. Now this is multiplied by another matrix called query key value, and the dimension of that matrix is 768 by 2304. Now you might be wondering, where is this 2304 coming? It is basically 768 multiplied by 3. So each of these matrices, query matrix is this, you can consider 3 sub-matrices: query submatrix, key submatrix, and value submatrix. I will explain what are these query, key, and value. Each of these are square matrices. So if this is 768, this will be 768, this will be 768, and this will be 768. That is why the QKV dimension here is 768 by 2304. Now we will multiply this matrix, this embedding matrix, with the query key value matrix. So this is 6 by 768 and this is 768 by 2304. And we will also add a bias. The bias is a matrix of dimension 2304. And the resultant dimension would be 6 by 2304. You would have already guessed this because there are 6 words. So 1, 2, 3, 4, 5, 6. There are 6 words. And this dimension is 2304 because this dimension is 2304. So now you have query key value for every single word in the sentence. Now, what exactly is this query key value? A simple analogy that is presented in the Poloclub example is that of a search engine. I am fully aware that these analogies are almost always insufficient to properly explain what is query key value. And in fact, in my experience, query key and value is the most difficult to understand concept within the entire transformer. So if at this part of the video you are feeling a little bit uneasy, just stay with me. No need to worry. Next parts are only easier than this. So query key value, you can imagine something like this. Let's say you are searching for something on Google. Your search query can be considered analogous to the query within this context. Search query means find, let's say I'm searching for video of match between Novak Djokovic and Roger Federer. That's my search query. Then key is basically the web page link. So there are a bunch of web page links that will show up when I search something like this on Google. Maybe the top link is that of YouTube, right? And when I click that link, I'm taken into the YouTube. So that web page link is the key. So search query is what I search, what I'm searching for. Key is where you can find info related to the search query. So if I search Novak Djokovic versus Roger Federer, I will find the info related to this query within the key. And what is this key? This key is a link to maybe a YouTube video. And what is the value? Value is what is contained within the actual website, meaning what is contained within YouTube. That itself is the value. So this analogy is very insufficient to properly understand the meaning of query key value. But at least you can imagine it to be something where each part, query, key, as well as value, has some role to play in this whole process of finding what you want to find, right? So what's happening here in this multi-head self-attention is this getting these query key value vectors. Now, how does it appear here? So let's go back to the transformer explainer. So I'll expand each of these sections. So first tokenization, then position in token embedding, then position encoding, and then you sum up these two things, right? And then you come to the multi-head self-attention. So why is it called multi-head self-attention? Multi-head because there are 12 such heads. What you are seeing in this screen is just one out of the 12 heads. In GPT-2, there are 12 heads. In other GPTs, there are 96 heads, depending on which GPT or which large language model you are looking at. So when somebody says self-attention, if you cannot imagine anything else, at least imagine a square matrix. If you have 6 tokens, imagine a 6x6 matrix, right? That's all you need to do. Now we will come to what exactly this 6x6 matrix looks like and why is it the attention. But before that, let's look at the QKV value creation process for each token. So I will just move my mouse pointer. I'll just click on this part so that you can see this animation. See what's happening here. Each token is getting multiplied with this QKV matrix to create a 2304 dimension version of the original 768 dimensional token. So why is it 2304? As I mentioned, it's 768 multiplied by 3. Now what happens is for every single token, so we have 6 tokens here, right? Data, visualization, M, powers, users, 2. There are 6 tokens, which means there are 6 query values and 6 key values. We do a dot product between them to get this attention matrix. So the query of data is done a dot product with the key of data. So that is this. Here, query of visualization is dotted with key of data. Here, do you see the color changing here? So when I move my mouse pointer from here to here, the blue color is changing from data to visualization over here. Just focus your attention here. I can also increase the zoom in, but then you will lose the entire picture. So here, query of data is dotted with key of data, query of visualization with key of data, query of M with key of data, query of powers with key of data, query of users with key of data, and so on. And here in the first column, the query remains data. The query matrix remains corresponding to that of data token. So query of data with key of data, query of data with key of visualization, then key of M, key of powers, key of users, and key of 2. So this is how this attention matrix is created. So now let's click on this. You see this dot product. Now, why does it show minus 25.3 to 7.4? Simply because that is the range of values. I think this one is 7.36, so rounded off to 7.4. And I think this is minus 25.29, which is rounded off to minus 25.3. Here, please note that value matrix is not coming into picture yet. We will come to that. Now, what is done is, I'll explain this through the blackboard. So once we have the query key value and once we calculate the attention, three things are done. First is calculating what is called as the attention score, which you already saw. It's this dot product. Now attention score is calculated using the dot product of Q and K, but it will have certain range of values. You saw the ranges from minus 25.3 to 7.4. This is just for this particular example. Obviously, the range will depend on the tokens that you are inputting. Now what we do is something called as masking. In the masking, what we do is we make the entire values of this triangle, upper triangle, into negative infinity. You will understand why that is done in a moment. So this whole triangle is converted into, the values are converted into negative infinity. So why is this done? In transformer, we are trying to predict the next word, right? So imagine I only input the word data. Then the transformer model should not have access to any other tokens. Like it should not have access to visualization. It should not have access to M, powers, users, to, etc. So it just has data. Then it will predict data itself. There is no next word prediction. But if data and visualization if both of these tokens are part of the training, then if data is the word that is provided, then visualization is the word that is to be predicted. It should not get access to M, powers, users, to, etc. So I'll explain that once again. Just pay attention. In the transformer training, when you are trying to predict the next word, you can first try to predict from the input data itself, because within input data itself, there are multiple words, multiple tokens. So if data is provided, the transformers can try to predict visualization. If visualization is provided, it can try to predict M. If data, visualization, and M is provided, it can try to predict powers, etc. So ideally in the training process, if data is provided, if data is only what is provided, it should not see the rest of the words. If data and visualization are provided, it should not see the rest of the other 4 words. Similarly, if the first 3 words are provided, it should not see the remaining 3 words, because it is trying to predict the next word. So the future words should not be visible to the transformer. So that is why here all these values, so in this row, only one value will be available. Rest of the values are assigned negative infinity. In the second row, only 2 values will be available. Rest of the values are assigned negative infinity. In the third row, 3 values are available. Remaining 3 are infinity. Fourth row, 4 are some values that are finite, last 2 are infinity. Now what is done is we apply softmax on each of these rows. What is softmax? If you are given a set of numbers, let's say 1, 2, 3, softmax will convert these numbers 1, 2, 3 into a probability distribution between 0 and 1, such that if you add the softmax of 1 plus softmax of 2 plus softmax of 3, you will get 1, because sum of probabilities should be 1. And the probability corresponding to the highest number, which is 3 in our example, will be the highest. So maybe softmax of 3 will be, I have to do the calculation, but let's say it is 0.6. Softmax of 2 among the numbers 1, 2, 3 is, let's say, 0.3. Then the softmax of 1 will be 0.1. So 0.6 plus 0.3 plus 0.1 will be equal to 1. So here, when you convert this row into softmax, all of these are negative infinity. So negative infinity is such a low number that it is essentially converted into 0. So all of these will be zeros and this will be equal to 1. So because there is only one number here, which is minus 0.52, all of the other numbers are negative infinity. Here there are 2 numbers, all of the other ones are negative infinity. So the softmax of all of these will be 0. All of these will be 0, but these 2 will sum up to 1. That's what you can see here, 0.84 and 0.16. So scaled masking. So dot product is masked here, and then it is converted into a softmax. So probability distribution. So each row is a softmax probability distribution whose sum, the sum of each row will be equal to 1. So sum of this is 1 because the first element is 1. There is only one element. In the second row, the sum of first two elements are 1 because there are only two elements, 0.84 plus 0.16. So here it is 0.63 plus 0.21 plus 0.16. Again, it is 1. Here, these 4 will add up to 1, these 4 will add up to 1, and these 5 will add up to 1, and these 6 will add up to 1. This is what the softmax does. It normalizes the set of numbers, and it also gives a probability distribution. So it is normalized between, 0 to 1, and the probability will be between, obviously, sum of the probabilities for each row will be 1. And so now what is the output of this whole attention head in a single layer? The output of the attention head is nothing but the multiplication of this softmax with the value matrix. So the value had 6 items, right? For data visualization, M powers users 2, there are 6 tokens. So it had 6 items. And here also, this is 6 by 6. And so you multiply this softmax output with the value to get the output of this multi-head attention layer. What you currently see is not a multi-head attention. This is a single head attention. But essentially, the same thing happens in the other 11 heads in the attention separately. So it's like a parallel computing. So there are 12 heads for GPT-2. In each head, this attention is calculated, then it is masked, then softmax is applied, then it is multiplied by the value matrix, and then you get the output. Okay, so now let's move on to the next part of the transformer model, which is nothing but multi-layer perceptron. This word is a bit scary, perceptron, like it's a scary word. It's simply just a feed-forward neural network, a normal neural network. This neural network does something very simple. And the purpose of this neural network is such that you can learn some things which you cannot learn in the attention layer. So it helps you create deeper meanings from whatever the attention layer is learning in the training process. So first, the input tokens, each of them are 768, right? The dimension of each input token is 768. It is upscaled into a dimension of 3072, so 4x, so 768 multiplied by 4. That is what happens in the first linear transformation. So I said there are 2 linear transformations happening. And not just that, there is also an activation happening. I'll mention what is it very briefly. I don't want you to visualize, oh, where is this activation happening and all that. But just understand that this guy, that was 768 is converted into 3072 over here. This is a vector. And then it is downscaled after activation into another, downscaled it back into 768. And this is done for all the 6 tokens. So there will be 768, 768, 768, 768, 768. Each of them are converted to 3072 and then scaled down by 1/4 back into 768. Let us go into the interactive module just to see what's happening here. So the multi-layer perceptron, I'm skipping some details over here like dropout and this residual connection, etc. It is very important concept. Residual connection ensures that, when there is a gradient descent happening from the output part to the input, this residual connection helps to make the gradient flow better. But I don't want to go into the details of this because that will kind of be out of the scope of this lecture, where I'm trying to oversimplify things, not like overcomplicate. And here is where the upscaling and downscaling happens in the multi-layer perceptron. Here also there is a residual connection, similar residual connection what you see here. It's also happening in the multi-layer perceptron, but just ignore it. Now we come to the part of prediction. But before coming to the prediction, let me just show you what is this JLU or GALU activation, Gaussian Error Linear Unit. ReLU, you might be familiar. ReLU activation is nothing but if the input is positive, the value is retained. So let's say ReLU of 3 is equal to 3. ReLU, which is rectified linear unit, ReLU of 3 is equal to 3. But ReLU of any negative number, R, I'll just write it as R of -3 equal to 0. So ReLU will convert all negative numbers to 0, as you can see here in this red plot, and all positive numbers as the input will be retained as such. ReLU is a very popular activation function, and these activation functions enable neural networks to learn non-linear relationships, right? Gelu is slightly different. The shape of Gelu is very similar to Relu. The only difference is it's much more smoother. So here the derivative of Relu at this point is discontinuous, right? So here the derivative from the left side is 0. Here the derivative from the right side is 1. But on the other hand, Gelu has a smooth derivative, so that is very good in terms of doing back propagation. But let's not go into the details of that. I want to go into the prediction part now, prediction of the next word. So now, how is the output probability predicted? Meaning, if there are 50,257 words within the vocabulary from which you can choose what should be the next word, how do you choose this next word? So first, something called as logits is created, and for this, only the last token is used. Meaning, for predicting the next word, data, visualization, M, powers, and users are not used. Only this 2 is used. So that's why here you see only 2 is mentioned. So 2 is used to create the output probability distribution from which you can pick the next word. So first, something called as logits is created. So logit is nothing but if a probability is given as the input. So if input is probability, it means the input is between 0 and 1. Logit will convert that into a range from -infinity to +infinity. So, and that's why you can see that there are large negative values here, and there might also be large positive values. We are not showing all the words here because there are 50,257 words in the vocabulary. You can only see like a handful of words here. And then logit is converted into an exponent. How is it done? You can see the formula here. So you click here and you hover on top of this. You can see that it is e raised to -135.9 divided by 1. Now you might be wondering, what is this divided by 1? I will come into that in a moment. So what is done is the last token, which is it in this case, it is 2, right? 2 in this case, is projected into this vocabulary space where there are 50,257 words. So that many dimensions. And every single token in this vocabulary, which means every single token in this 50,257 tokens are converted into corresponding logits. Then logits are converted into an exponent. So logit is converted into an exponent. Exponent is converted into a softmax. So softmax is where we get the probability distribution. So now let us look at this logit part. Let's focus on this. If you are watching this video on phone, you might want to zoom in using your hand a little bit because these numbers are a bit small. I can also increase the size here a little bit, maybe if that helps. But basically, I hope it is visible. Otherwise, try just to zoom in. So here, the tokens within the vocabulary is converted into logits. And logits is converted into exponent using this formula, exponential of whatever is the logit divided by 1. Here 1 is something called as temperature. So let me zoom out to show you the temperature. So this is the temperature. What is temperature actually? Let's say the temperature is very high, or rather very low. It's 0.2. You can see what's happening to this output probability distribution in the softmax. And in the calculation, if temperature is 0.2, here the formula of the exponent is exponent of logit divided by 0.2. So basically, the logit is divided by the value of temperature. By default, the temperature would be 1, meaning the logit is divided by 1, meaning softmax is not affected. The logit is divided by 1, -135.9 is divided by 1, and we are taking the exponent of that. So exponent of -135.91 divided by 1. I'll just write it so that it's clear to you. So here exponent is calculated as e raised to -135.91 divided by t, where t is the temperature. So if t equal to 1, then the softmax is not affected. But if t is greater than 1, softmax is affected. T is less than 1, meaning also softmax is affected. Now, how is it affected? This is very interesting. You might also notice this if you have tried to run ChatGPT using API. You can set this temperature parameter.